Aishwarya from Sri Venkateswara College of Engineering. Today in this about backtracking. Introduction to backtracking. Backtracking is a problem-solving algorithm that incrementally builds candidates for solution. It abandons a candidate as soon as it determines that the candidate cannot lead to a valid solution. This technique is commonly used in combinational problems like puzzles, pathfinding, and constraint satisfaction. A given problem has a set of constraints and possibly an objective function. The solution optimizes an objective function and or is feasible. We can represent the solution space for the problem using a state space tree. The root of the tree represents zero choices. Nodes at depth 1 represents first choice. Nodes at depth 2 represent the second choice. In this tree, a path from a root to a leaf represents a candidate solution. Backtracking algorithm principles. The backtracking algorithm explores all potential solutions to find the correct one. It systematically searches through the solution space while avoiding unnecessary work. The depth-first search approach is often used in backtracking to traverse possible solutions. Programming language overview. Ada is a high-level programming language designed for reliability and maintainability. It supports strong typing, modular programming, and concurrency, making it suitable for large systems. Backtracking can be efficiently implemented in Ada due to its structured features and controlled constructs. Components of backtracking. The main components include the recursive function, a solution space, and constraints. Recursive functions facilitate the exploration of potential solutions through the call stack. Constraints help in pruning the search space, eliminating invalid candidates early in the process. Recursive function structure. A typical recursive function for backtracking includes a base case and recursive calls. The base case checks if a valid solution has been found or if all options are exhausted. Recursive calls explore further possibilities by modifying the state based on the current choice. Example problem: n queens. The n queens problem is a classic backtracking example where n queens must be placed on an n cross n chessboard. The goal is to place all queens such that no two queens threaten each other. Backtracking is used to explore different arrangements backtracking when a conflict is detected. The problem is to place n queens on an n by n board so that no two queens are in the same row, column, or diagonal. The 4 by 4 board above shows a solution for n equals 4. The text gives an explicit construction for a solution for each n greater than or equal to 4. But first, we will introduce an algorithm strategy called backtracking, which can be used to construct all solutions for a given n. N means implementation. The implementation begins by defining the board and a recursive function to place queens. Each recursive call attempts to place a queen in a valid position and proceeds to the next row. If a position leads to no valid placements, the function backtracks to try the next position. Visualization of backtracking. Visualizing the backtracking process helps in understanding the search space. Each decision point can be represented as a node in a tree structure. Pruning occurs when branches are cut off, leading to more efficient searches. Constraints in backtracking. Constraints are conditions that must be satisfied for a candidate solution to be valid. They help eliminate paths that do not lead to a solution early in the process. In Ada, constraints can become implemented using conditional statements and flags. Handling state. Managing state effectively is crucial in backtracking implementations. State can be represented using arrays, records, or other data structures in Ada. The state must be updated correctly as the algorithm explores different paths. Performance considerations. The time complexity of backtracking algorithms can be significant, often exponential. Effective pruning and constraint propagation can improve performance. Profiling and optimizing the recursive function can lead to faster solutions. Backtracking versus brute force. Backtracking is often more efficient than brute force. search due to its pruning capabilities, while brute force explores all possibilities indiscriminately. Backtracking eliminates invalid paths. This makes backtracking more suitable for complex problems with large solution space. Practical applications of backtracking. Backtracking is widely used in games, puzzles, and optimization problems. It can solve problems like Sudoku, the traveling salesman, and graph coloring. Many AI algorithms also employ backtracking for decision-making process. Debugging backtracking algorithms. Debugging can be challenged due to the recursive nature of backtracking. Adding logging or visual output at each decision point can help trace the algorithm's behavior. Testing against known solutions can validate the correctness of the implementation. Handling multiple solutions. Some problems may have multiple valid solutions that backtracking can find. To find all solutions, the algorithm can continue searching after finding a valid one. This requires careful management of the state to avoid duplicates. Backtracking. Backtracking may become impractical for very large search spaces due to time constraints. It can also struggle with problems that lack efficient constraints for pruning. Understanding the problem domain is essential for effectively applying backtracking. Future directions in backtracking. Research in backtracking continues to evolve, focusing on improved algorithms and heuristics. Hybrid approaches combining backtracking with other techniques are being explored. ADAS features can be utilized for developing advanced backtracking solutions in various domains. Conclusion. Backtracking is a powerful algorithmic technique for solving complex problems. ADA provides a robust framework for implementing backtracking solutions effectively. Understanding and applying backtracking can lead to significant improvements in problem-solving capabilities. Let us see some disadvantages of backtracking. Backtracking approach is not efficient for solving strategic problems. The overall runtime of backtracking algorithm is normally slow. To solve large problems, sometimes it needs to take the help of other techniques like branch and bound. Need large amount of memory space for storing different state function in the stack for big problem. Thrashing is one of the main problem of backtracking. The basic approach detects the conflicts too late. Thank you.